Back with the video. Okay. um, I hope guys you are not finding much difficulty with this. I repeat myself in every video that if you are having facing any problems, please let me know. Okay. So I'm actually sharing my links with Madiha, and she will share the links in our pattern recognition class, so all must see that. So what we have done is actually, in the last video we had done two category classification. Now with this video we are actually starting minimum error rate classification. Okay. So guys, again, you please go to that particular portion of PDF where it is minimum error rate classification. So some parts I am going to skip, some derivations I am going to skip, and those derivations are not coming for your exam. Later we can study in extra classes, or you can also study by yourself or some other person. But for now, time being, for semester exam, whatever I'm going to study out or read out, that is important. Okay. Um, so minimum error rate classification, I'm going to read out. Please follow the PDF. So first we are going to get it through is actually 0 1 loss function. Okay. In classification problem, each state of nature is usually associated with a different one of the C classes. Okay. And the action alpha I is usually interpreted as the decision that the true state of nature is omega I. Yes, you know that when action is alpha I and true state of nature is omega I, that means what? Means the feature x bar, we are classifying it under omega I. Okay. So the action is alpha I, which is the correct decision, which is not the ideal case. Okay. Which is the in fact the ideal case, which we are not going to consider. So our thing will be actually alpha I and lambda j, and then alpha I and omega j, and as soon as alpha I and omega j comes, we immediately have the loss function because I and j are two different. Okay. Now the more is the distance, or the more is the difference between I and j, this lambda increases. Okay. And the less is the distance or the difference, this lambda value decreases. So our principal target is to set the this value of I. This omega j we cannot change because slash on the right side of the slash, this omega is situated. That means it is actually, this class is given. This class is given. Okay, you cannot change this class. But this alpha I, this you can change this one. Okay, the means whatever alpha I or whatever action you are going to choose, based on that this lambda is going to reduce or increase. Now, again we come back. If action alpha I is taken and the true state of nature is omega j, then the decision is correct if and only if I is equal to j. If I is equal to j, then decision is correct. And error, and if there will be error, means of the loss function if I not equal to j. This I was already talking about since last two videos. The errors are to be avoided. Okay, fine. It's always natural. We always try to avoid the error. It is natural to seek a decision rule that minimizes the probability of error. Very good. That is the error rate. Okay. The loss function of interest for this case is called the symmetrical or 0 1 loss function. So we introduce a new term which is called symmetrical or 0 1 loss function. What it is? Symmetrical or 0 1 loss function. Okay. So what did it say? Lambda, you know the loss function how it looks like. Now you must be accustomed to it. Lambda alpha I slash omega j. Now from this portion, I'm not going to explain this term again and again. Okay. Already in the last two videos, I've explained this thing many times. So this we can also, I also told you that you can substitute this by lambda ij. That is an easier. This is only a notation. Note that this thing and this thing is same. Already in the last video, I've explained it. So lambda alpha I omega j, that is equal to either 0 or 1. Okay. It will be 0 if and only if I is equal to j. That means alpha I is equal to omega I, or alpha I slash alpha j slash omega j if I is equal to j. Because because you have taken the correct decision. You have taken the correct decision, and so there is no loss. So the loss function value is 0. But it is equal to 1 if I not equal to j. Very correct. If I is not equal to j, that means you have taken wrong decision. So the loss function, 0 1 loss function or the symmetrical loss function will evaluate this full lambda to 1. Note that uh, in the last case, I had told you one thing, that you try to minimize this thing. 0, 1 loss function will always give the value as 1 if even if there is slight difference between I and j. Suppose the value of I is 2 and the j's value is 3. Okay. Then also it will become alpha to omega 3. Then also it is 1. And if it is alpha to omega 100, then also 1. Like if the difference between I and j is very big, then also lambda alpha omega j is 1 in case of 0, 1 loss function. Okay. And if it is very small, say alpha 45 omega 46, then also the value will be evaluated to 1. This is the speciality of 0, 1 loss function, that over here we are not considering that the difference of I and j is big or difference of I and j is small. No, in 0, 1 loss function or symmetrical loss function, even if there is a slight difference between I and j, the value will be evaluated to 1. Only if I is equal to j, then it is evaluated to 0. Okay. So I hope this portion is clear. So I'm going to rub this part now. So now from here I start reading. This loss function assigns no loss to a correct decision and assigns a unit loss to any error. Okay, even if it is slight error, then also it will assign it to 1. That is, all the errors are treated as equally costly, means all the errors will be treated with equal importance. Okay. The risk corresponding to this loss function is precisely the average probability of error, because the conditional risk is. Now we go for another derivation. Just follow the PDF. I start writing it over here. Now guys, you already in the last class I have already said you that our alpha I slash on x bar is equal to summation over of j1 to c lambda alpha I omega j and p omega j slash x. Okay. So r alpha I slash x bar is equal to summation over of j is equal to 1 to c. So we had in the last expected loss only we have derived this lambda alpha I slash omega j p omega j slash x bar. This was the thing we have derived. Now we are now considering loss. No, means it's not the ideal case. Means ideal case, if I equal to j, then this will become 0 and anything multiplied by 0 is 0. So this expected loss will be 0. Now we are considering that case where this I is not equal to j. For I is not equal to j, immediately this 0, 1 loss function or symmetrical loss function will produce this value as 1. So lambda alpha I omega j will become 1. And we know that if this becomes 1, anything multiplied by 1 will give back that term. So we will have summation over of j not equal to I. This is only valid when j is not equal to I. If j is equal to I, then this thing becomes 0. So this term becomes 1. This term becomes 1 in case of with if you consider 0, 1 loss function, that is equal to p omega I posterior probability x bar. So only this term remains. Is it clear? Now we already know that summation of all probabilities is equal to always 1. Okay. So p omega I slash x bar plus p omega j slash x bar was also 1. So with p omega summation of all p omega I slash x bar, that I can write it as, sorry, this is omega j. Okay. So summation of all p omega j slash x bar. Now p omega j summation of p omega j slash x bar plus p omega I slash x bar was equal to 1. We know that sum of all the probabilities is equal to 1. So if I take only summation of p omega j slash x bar, I can write it as 1 minus p omega I slash x bar. I can write it like this for all j not equal to I. This portion I am explaining once again. summation of all p omega j slash x bar plus p omega I slash x bar was equal to 1. This is the theory from theory of probability. Now if I keep, now over here we have only this term, summation of all p omega j slash x bar for all j not equal to I. So I can write it as 1 minus p omega I slash x bar. So this is my equation 20. You can mark it. So let's me start reading. The risk corresponding to this loss function is precisely the average probability of error, because the conditional risk is p omega I slash x bar is the conditional probability that the action alpha is correct. The Bayes decision rule to minimize risk calls for selecting the action that minimizes the conditional risk. Thus, to minimize the average probability of error, we should select the I, means we should select such an I that maximize the posterior probability p omega I slash x bar. So if this p omega I slash x bar becomes maximum, okay, this entire terms become minimum. See, this is actually from any arithmetic. This we can means prove from any arithmetical logic, normal mathematical logic, the substantiate from any normal mathematical logic, that if 1 minus something, okay, so if the second term becomes maximized, okay, then what will happen? This 1 minus something is going to get minimized, and if this is becomes minimized, then this becomes minimized. If this becomes minimized, then this becomes minimized. So in order to minimize the expected loss, this term must be maximized. This is the conclusion. Okay, you write down this line, please. This is a very important line. The Bayes decision rule to minimize risk calls for selecting the action that minimizes the conditional risk. This risk must be minimized. In order to minimize this thing, this must be minimized. So when will it become minimized? If this is maximized. Okay. Thus, to minimize the average probability of error, means this average probability of error, we should select that I, that particular I should be selected, okay, that maximizes the posterior probability. This probability maximized, p omega I slash x bar, this must be maximized. In other words, for minimum error rate, in order to get minimum error rate, decide omega I. So, from this I write, decide omega I if p omega I slash x bar is greater than p omega j slash x bar. So decide omega I means what? Action alpha I. If p omega I slash x bar is greater than p omega j slash x bar for all I not equal to j. Okay, because if this is maximized, if this is greater, then 1 minus this will become less. So if 1 minus this will become less, so summation of this will become more, and then you can conclude that action alpha I will be taken, or the decision will be in favor of omega I, or the conditional risk will be minimized in such a case. If you take decision in favor of omega I, the conditional risk will be minimized, and that is our goal. Okay, this figure is not so important. We will come back to this figure later on. Actually, in this figure, you see there is a figure 2.3. Actually, there are 4, means it is divided into 2 regions, R1 and R2. This is also has got some correlation with 2 class problem. For all decisions to be taken in favor of class omega 1, okay, we divide the feature space into region 1, okay, R1. And for all decisions, that is alpha 2, to be taken in favor of omega 2, we divide the feature space into another region, which is R2. This is that nothing but R1 and R2. We will study this figure if it is necessary later on. So please guys, go through this video once very carefully. It's important. And then I will now start minimax criteria in this video itself. Please go through this once. In minimax criteria also, not all derivations are necessary. So this first paragraph, you can read it by yourself. See, minimax criteria, the first paragraph, please guys read it by yourself, and it's means just some basic logic which we have already discussed. Okay, I start from the second paragraph. Minimax criteria, please follow the PDF. I start from the second paragraph. So, now this minimax criteria, in order to understand this, let R1 denote whatever I said, region in feature space. Feature space means a space, a 3D space comprising of feature vectors. Okay, that's feature space. Region is feature space where the classifier decides omega 1 and likewise R2 for omega 2. Means classifier decides omega 1 means classifier is acting like actually the algorithm or the function, isn't it? Which will help you to take action alpha I. So this R1 is where decision or alpha I will take, decision will be taken in favor of omega I. Okay, and R2 is, sorry, in omega 1 or and alpha 2, and R2 is for alpha 2 where decision will be taken in favor of omega 2 and omega 2, and then let us write down the overall risk equation 12 in terms of conditional risks. Okay, so what was equation 12? It was, let's have a look, R, this equation, R is equal to summation of R alpha x, already these things I've explained, I'm not going to repeat them again. Okay, px, and we have this dx for this integration sign. Okay, now this equation 12, I'm going to rewrite it. So in case of region 1 and region 2, it will be, if I now consider the loss functions, do you remember the loss functions? So for region, this R is the overall risk. Okay, now I am going to split it up into two places. One is R1 and another one is R2. So for R1 we will have the loss function both for class omega 1 and class omega 2, and for R2 also we will have the loss function both for class omega 1 and omega 2. Is it clear? So first let me split this R into region R1. So it will become, if I write it like this, R1. Okay, so I start with lambda 1 1. Lambda 1 1 means, you know, now I'm ij. Okay, that means lambda ij means alpha I slash omega j. Okay, p omega 1 dot p x bar slash omega 1. This we are derived from Bayes formula, that is the posterior probability product of prior and likelihood. Okay, plus lambda 1 to p omega 2 dot p x bar slash omega 2 dx. This is dx. Okay, this is for region R1. So R is equal to, first part is R1. So lambda 1 1 p omega 1 dot p x bar slash omega 1 plus lambda 1 2 p omega 2 dot p x bar slash omega 2 dx. This dx is for this integration sign. So for region R1 we are done. Okay, see, in region R1 we have both for omega 1 as well as for omega 2. Similarly, now in region R2 also we will have this thing for both omega 1 and omega 2. So it will become lambda 2 1 p omega 1 dot p x bar slash omega 1 plus lambda 2 2 p omega 2 dot p x bar slash omega 2 dx. So this is my total R. This is my total R. What is my total R? Lambda 1 1. This first is region R1. Okay, where decision will be taken in favor of omega 1. So how do we conclude that decision will be taken in favor of omega? We have to keep both the classes omega 1 and omega 2, but we are going to take in decision in favor of omega 1. This is my region R1. Lambda 1 1 dot p omega 1 dot p x bar slash omega 1 plus lambda 1 2 p omega 2 dot p omega x bar slash omega 2 dx. Okay. Now this region R2, again we will have both for omega 1 and omega 2, but decision over here will be taken in favor of omega 2. So we will have lambda 2 1 dot p omega j dot p omega 1 dot p x bar slash omega 1 plus lambda 2 2 p omega 2 dot p x bar slash omega 2 dx. So these are the two. Okay. Now from here we are going to write. So this part is clear. You can also see from the PDF. I have to rub the blackboard, guys. Okay. So now I'm going to rub this entire thing off. Okay. Now again we can use the fact that we know that summation of all the p omega 1 plus p omega 2 is equal to 1. This we have already studied before, that summation of all probabilities is 1. So p omega 2 is equal to 1 minus of p omega 1. Okay. And that region of R1, so from this we can now say region of R1 p x bar omega 1 p x bar omega 1 dx is equal to 1 minus of region R2 p x bar omega 2 dx. Summation of all probabilities is equal to 1. If p omega 2 equal to p omega 1, 1 minus p omega 1, then just keep the region R1 on this side. Just keep the likelihood, okay, R1 p x bar slash omega 1 dx, that is equal to 1 minus of R2 p x bar slash omega 2 dx. Just follow this one. P omega 2 equal to 1 minus p omega 1. If I keep p omega 1 this side, then it will be p omega 1 equal to 1 minus p omega 2. So region R1 p x bar slash omega 1 dx, that will be equal to 1 minus of region R2 p x bar slash omega 2 dx. Is it clear? Now from this we are going to have a very big derivation. Okay, this you can just simply memorize. You don't need the entire process to do. But just we have to memorize this derivation, means the formula, the final formula, minimum risk, we have to simply memorize that. After that we shall go to classifiers. Niemann-Pearson criterion, that's not in your syllabus, so don't have to bother your mind on that. So I rub this. Now from here I write this thing. It's a very big derivation, guys. Please you try to follow the PDF first, okay, and then you can follow the blackboard also, because in PDF it is very clearly given. R function of p omega 1, okay, that is equal to lambda 2 2 plus lambda 1 2 minus lambda 2 2 summation of R1 p x bar slash omega 2 dx. Okay, this is one term. This is one term of the entire formula, plus this is the second term. I don't have space over here, so I write it down over here. Plus p omega 1, then I keep a third bracket, okay, lambda 1 1 minus lambda 2 2 plus again lambda 2 1 minus lambda 1 1. Okay, this again I have to split it over here also, because I don't have much space over here. Summation of again region 2 p x bar slash omega 1 dx. Okay, Then this third bracket is still continuing. Okay, this third bracket, it is multiplied by p omega 1. Again, we have another term over here. This term falls under this third bracket. Okay, minus lambda 1 2 minus lambda 2 2 summation of region 1 p x bar slash omega 2 dx. So, this is the entire risk. Okay. So I write the overall risks are p omega 1. I repeat this formula. First we have one term lambda 2 2 plus, okay, the second term lambda 1 2 minus lambda 2 2 multiplied by integration r1 p x bar slash omega 2 dx. This constitutes my first term. Okay. Now it is continuing here plus p omega 1, and then I have a third bracket which ends over here. So I have a big term inside the third bracket which is lambda 1 1 minus lambda 2 2 plus lambda 2 1 minus lambda 1 1 integration of r2 dx bar omega 1 dx minus lambda 1 2 minus lambda 2 2 region r1 px bar slash omega 2 dx. Okay. This is my entire risk. Okay. Now this particular term, see, I'm going to mark, it's also given in the book. This entire term from here to here, okay, is called as RMM or minimum risk. Okay. This minimax risk, sorry, RMM, this is also called minimax risk. This is also called minimax risk. Okay. RMM is called minimax risk, and in order to achieve minimax solution, this entire term in third bracket have to become 0. Whatever is inside this third bracket multiplied by p omega 1, if you can equate this entire thing, okay, to 0, then this will give you the minimax solution. The equation shows that once the decision boundary is set, so R1 was for region 1, this is the decision boundary where decision will be taken in favor of omega 1, and R2 is the region boundary for omega 2 where decision will be taken in favor of omega 2. This equation shows that once the decision boundary is set, that is R1 and R2 determined, okay, the overall risk is linear in p omega 1, of course, because this term will become 0. If we can find a boundary such that the constant proportionality is 0, then the risk is independent of priors. See, if this becomes 0, then there is no prior term. Okay, there is only p x bar slash omega 2. There is no prior term. This is the minimax solution. So when this particular term will become 0, this r p omega 1 will give you the minimax solution, and the and the minimax risk is already explained, RMM. This portion is called minimax risk, and in order to make this r p omega 1 as for the minimax solution, this entire term have to become equal to 0. Okay. This is the minimax solution, and the minimax risk is RMM and can be read from equation 23. So what it will become? Lambda 2 2 plus lambda 1 2 minus lambda 2 2 r1 px bar omega 2 dx, that is equal to lambda 1 1. Okay, I write it down. So this equation, I hope this is clear. You have to memorize this thing. There is a huge derivation for this, okay, and you don't need that for your current semester. They will not be given in your current semester. So I just skip the derivation. I just give you the what is the minimax risk, and for minimax solution, this entire term has to become 0 in order to make this for the minimax solution. Okay. Now, just we focus on this term. Considering that r p omega 1 is minimax solution. Minimax solution means this term is 0. So anything multiplied by 0 is 0. So if you multiply p omega 1 by into 0, then it will become 0. And so r p omega 1 will be only this RMM, this portion. Okay. Now we are going to focus on this portion only. So I rub this thing. Just focus on this portion, means this particular thing, not this one, because this is 0 for minimax solution. So what will I have? RMM is equal to, just I write that RMM part, okay? That is equal to lambda 2 2. Lambda 2 2, it was there already. Just you can have lambda 1 2 minus lambda 2 to region R1, decision boundary for where decision will be in favor of omega 1, that is equal to P x bar omega 2 dx. That is equal to, again, if you write it in terms of omega 1, then what will it become? Lambda 1 1 plus lambda 2 1 minus lambda 1 1 R2 P x bar slash omega 1 dx. These two are same. You are expressing means RMM, okay. If in terms of region 1, you are expressing where decision will be taken in favor of omega 1, this will be the thing. And if you are expressing it in terms of region 2, this will be the thing. The value of the minimum risk RMM is hence equal to the worst bias risk. In practice, finding the decision boundary for minimax risk may be difficult, particularly when distribution are complicated. Anyways, leave this part, not necessary. Then we have Niemann-Pearson criteria. I already told you that it is not included in your syllabus. So next we will be going to classify discriminant function and decision surfaces. Thank you.